Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 1.2, Solutions to Ordinary Differential Equations. In Chapter 1.2, we now look at what an explicit solution to a differential equation looks like. In some cases, when explicit solutions of a differential equation is unobtainable, we will then look for properties of solutions from differential equations using direction fields. We call this a qualitative approach. To get started, let's look at some definitions. A differential equation, or a DE, is an equation that contains some unknown function and one or more of its derivatives. In this chapter, we are going to focus on first-order differential equations, equations that have just the first derivative, that can be written in one of these forms. An analytic solution to a differential equation is a function y of t that satisfies the differential equation for the appropriate value of t. An initial value problem, sometimes written as an IVP, is a combination of a first-order differential equation and an initial condition that it must go through. An autonomous differential equation is a DE that does not depend on time. This means that it can be written in the form y prime is only a function of y, because the variable t will not show up in the differential equation. Let's look at an example to get started. Consider the differential equation y prime is equal to 2y. And we are asked to verify, or to find, which of these three functions are solutions. The way we're going to verify if a function is a solution is by direct substitution. So let's try these one at a time. Let's consider y equals the function e to the t. And we want to know, does this satisfy this differential equation? So let's imagine taking our differential equation, y prime equals 2y, and by direct substitution, we'll see if both sides of this equation are equal. So the derivative of e to the t, we know, is e to the t. Is this equal to 2 times the original function? So is this equal to 2 times e to the t? And clearly we can see that these are not equal. So we can say that y equals e to the t is not a solution. Let's look at our next function. Is y equal e to the 2t a solution? Again, to see if this is a solution, we'll take our original differential equation, y prime equals 2y. And by direct substitution, let's see if both sides of this equation will be equal. So the left side, the derivative. The derivative of e to the 2t is going to be e to the 2t. Then by the chain rule, the derivative of 2t will be 2. Is this equal to 2 times the original function? And we'll say yes, and so we will be able to conclude y equals e to the 2t is a solution. I'd like you to take a moment now and verify if the third one, y equals 3e to the 2t, is a solution. And if you could, please pause the video for a moment while you verify if this is a solution. After you're done, come back and we'll see if we agree. Okay, I hope you paused the video and worked on this. Let's see if we have the same solution. Left-hand side, we'll take the derivative of the proposed function. Here, the derivative of 3e to the 2t, we'll do the e to the 2t. The derivative of e to the 2t is e to the 2t times by the chain rule, a 2, which will make the front coefficient be a 6. And we're asking, is this going to be equal to 2 times our original function? And we can verify by multiplication that these are equal, which tells us y equals 3e to the 2t is also a solution to the differential equation. In future sections, we'll actually be able to verify that there are many other solutions that match these two in form. In general, we'll be able to say solutions to this differential equation will always look like c e to the 2t, where c can be any constant. Notice that both of these are of that form. However, for chapter 1.2, we're asked just to be able to verify solutions of differential equations, and we're intended to do it by direct substitution like we are now. Let's look at another example. Consider the differential equation y prime is 1 over t times y plus t. Is this a solution to the differential equation? So to verify the solution, I want to be able to plug it into the DE and make sure that both sides are going to be the same. So let's do the left-hand side first. So here we're going to take the derivative of 3t plus t squared. And we're going to ask, is it equal to the right side of the differential equation? Will evaluating 1 over t times 3t plus t squared plus t, will it be the same? Are these going to be equal? Okay, so left-hand side, we'll take the derivative. Now the derivative of 3t plus t squared we know is 3 plus 2t. Right-hand side, here we probably want to do some algebraic simplification. Maybe distribute the 1 over t into the parentheses. 1 over t times 3t would be 3. 1 over t times t squared would be t. Plus t. Notice that if we simplify this, this will be 3 plus 2t. This tells us that y equals 3t plus t squared is a solution to the differential equation. Okay, let's try another one. I'd like to take a moment to give you some time to work on this on your own. So if you could, please pause the video and verify if y equals t squared plus natural log of t is a solution to this differential equation using direct substitution. After you finish, unpause the video and we'll verify if we get the same result. I'll see you in a moment. Okay, let's see how you did. So by direct substitution, I want to look at both the left and the right hand sides of the DE and see if they're going to be equal for this solution. So the left hand side, we want to look at y prime. So we want to look at the derivative of t squared natural log of t. Here, applying the product rule, we'll look at the derivative of t squared, which is going to be 2t times your second function, natural log of t, plus by the product rule, the derivative of your second function, the derivative of natural log of t, is 1 over t times your first function. You'll probably want to simplify this a little bit and write it as 2t natural log of t plus t. Now let's look at the right-hand side. The right-hand side, we have 2y divided by t plus t. And we're going to evaluate this at our proposed solution. So let's replace y with t squared natural log of t divided by t plus t. Again, I'm going to simplify this a little bit. Notice that on this first fraction, the t squared and the t will cancel, leaving just a single factor of t on the top. So this will be 2t natural log of t plus t. Here you want to notice that both the left hand and the right hand sides are both the same. This tells us that this is a solution to the DE. I hope you were able to verify this as well. Let's look at another kind of problem. What do solutions to this differential equation look like? Now here I'm not giving you a solution. I'm just asking you to verify to come up with what you think solutions will look like. And what I would like you to do here is be able to recall some techniques from calculus. So here we have y prime is equal to 3t squared. And I want you to help me come up with a function whose derivative is 3t squared. I'd like you to help me come up with the antiderivative. And from what we know from Calc 1 and Calc 2, we recognize that an antiderivative would have to be t cubed. However, this is not the only antiderivative. In general, we could add any constant, and this would also be an antiderivative. Remember, this is referred to as a family of antiderivatives. Now, in this problem, I want you to imagine, what do these solutions look like? And recall from algebra, we recognize that this constant c represents a vertical shift. Of the function t cubed. So if, for example, c is equal to 0, if c is equal to 0, then our function is just y equals t cubed. If, however, our constant c is equal to 2, so 1, 2, then our solution would look more like this. What you'd like to observe is that both of these have the same derivative. Y equals t cubed, the derivative would be 3t squared. Y equals t cubed plus 2, the derivative would still be 3t squared. So observe that when I give you a differential equation, there can be an infinite number of solutions that could vary by a constant. So from this example, what we would like to notice represents a family of solutions that differ by a constant. Every value of c gives a different function that will satisfy the differential equation. Let's look at another example. Can we find a solution to the initial value problem, 3t squared, y prime is 3t squared, that must go through the point 0, 4? So from our last example, we know there are an infinite number of solutions to the differential equation y prime is 3t squared that differ by a constant. And so in this example, I'm asking, what would the constant have to be so that our solution went through the point 0, 4? So we know that if y prime is equal to 3t squared, then a family of solutions looks like y of t is equal to t cubed plus c. Here, we require y of 0 to equal 4. So then y of 0 would be 0 cubed plus c, which we know is just c, and we require this to equal 4. This tells us what the value of c must be for our initial value problem. Let's make sure we write down our solution, though. Our solution is going to be y of t is equal to t cubed plus 4. This is a solution to the differential equation that also goes through this coordinate 0, 4. Let's look at another couple examples. There's 2 more here that are very similar. I'll work the first one with you and then leave the second one for you to do. Here we would like to verify that y equals 1/2 e to the negative t minus e to the negative 3t is a solution to this initial value problem. To be a solution to initial value problem, you have to do 2 things. You have to satisfy the differential equation, and you have to satisfy the initial condition. You must satisfy both requirements. It doesn't matter which one you do first, but if you were to fail one of them, then you would not be a solution to the initial value problem. Let's look at the initial condition first. To be a solution to the IVP, y of t must satisfy the initial condition. Okay, so let's evaluate this at our proposed function, our proposed solution, at 0. So here we have y of 0 would equal 1/2 e to the negative 0 minus e to the negative 3 times 0. Remember, e to the 0 is always 1, so this will be 1/2 minus 1, which is negative 1/2. So check. This does at least satisfy the initial condition. 2. To be a solution to the IVP, y of t must satisfy the DE. So let's verify that it satisfies the DE. So here we want to evaluate our proposed solution into our differential equation. So here we're going to have y prime. So we're going to have 1/2 e to the negative t minus e to the negative 3t. We'll take that derivative and add it to 3 times the original function. So 1/2 e to the negative t minus e to the negative 3t. And we're going to verify that this ends up equaling e to the negative t when we're done. So let's take some derivatives. The derivative of the difference of 2 functions is the difference of the derivatives. The derivative of the first function, e to the negative t, would be negative 1/2 e to the negative t. The derivative of e to the negative 3t is e to the negative 3t times by the chain rule. The derivative of this top, which would be negative 3, would turn this into plus 3 e to the negative 3t. For this second group, we can distribute this 3 into the parentheses. This would be plus 3/2 e to the negative t minus 3e to the negative 3t Now let's combine like terms. So here, if you combine the negative 1/2 e to the negative t and the 3/2 e to the negative t, this will just be e to the negative t. And when you combine the 3e to the negative 3t and the negative 3e to the negative 3t, notice that these are opposites and they cancel. So we verify that, so that we end up with just e to the negative 3t, which is equal to the right-hand side. This tells us that this satisfies the differential equation, and it satisfied the initial condition, so we know that this is a solution to the IVP. In general, you need to make sure that it satisfies both conditions. Okay. Now for this next example, I'd like to give you a moment to work on your own, so I'm going to ask that you pause the video. While your video is paused, I am going to work the solution as well, and I'm going to work it in a similar fashion to what I did on our previous example so that you can verify we get the same solution. So please pause the video now. I will see you in a moment after you've worked through the solution. I'll see you in a moment. Okay, I hope you went ahead and worked through this example. I did as well. You can see how I worked out my two solutions. Or two parts of the solution. I first wanted to verify that it satisfied the initial conditions, which I verified that it does. And then I verified that it must satisfy the differential equation, which it does. So in conclusion, we can say yes, y equals negative t minus 1 plus 5e to the t is a solution to this IVP. And I want to emphasize this IVP because if I were to change the initial condition, it might not have worked. If I had required this to go through the point 0.8, then this solution would have not gone through 0.8. So again, notice that your solution will not satisfy every initial value problem, but it does satisfy this initial value problem. Okay, let's move on to the next page and see what else we can do. Okay, the next thing we want to look at now is our qualitative analysis of differential equations. So historically, the study of differential equations was to find explicit analytic solutions. However, this can be difficult or impossible. In fact, we can only find explicit analytic solutions for certain types of differential equations. So now, in this chapter, we will shift our approach to be able to describe the qualitative behavior of solutions over time. So, first definition, a direction field, also called a D field or a slope field, is used to qualitatively, graphically, describe the behavior of the solutions of differential equations over time. These direction fields will show the slope of the solutions that would satisfy the differential equation. And here you can see an image that is what a typical direction field looks like, where each of these little red lines would represent the slope of a proposed solution, where each of the black lines is a different solution or a different member of the family of solutions. To create these direction fields, we create what's referred to as a discretization of the plane. We break the plane into a bunch of points. Then we evaluate the DE at each point in the plane and draw a little tangent line through that ordered pair. This first two steps is what creates all of the red line segments here. Afterward, we draw a solution curve that must agree with each of the slope field elements. So typically when I draw these black solution curves, I imagine the red lines as like the current in the water. And if you were to drop a leaf, it would follow the trend of the little red line segments. And so this is what a typical solution would look like. Let's practice this with an example. Here I want to create a direction field for the differential equation y prime is negative y. And I've already created the discretization of the plane for us. So now, to create the slope field, we want to find what would the slope of a little tangent line look like for each one of these points. And the way you do that is you would just evaluate your differential equation at the ordered pair in question. Now, in this example, we're talking about an autonomous differential equation. Remember, autonomous meant it was independent of time. Whereas in my second example I give you down here, this one is non-autonomous because t does appear in the differential equation. Now the difference that we want to notice is that the autonomous ones are dramatically easier because your differential equation, your slope, only depends on the y value. So when we start drawing our slope field elements, for example, if we pick 0, 0, our differential equation only depends on the y coordinate. So even though the ordered pair is 0, 0, all we use is the y coordinate, which says the slope at 0, 0 would have to be 0 and would look like this. If we pick the ordered pair 1, 0, again, the ordered pair 1, 0, I want to find the slope here, but since our differential equation only depends on y, I only use the y value, in which case the slope here would be 0 still. In fact, the slope would be 0 for everything along the x-axis where y is 0. Okay. If we pick any coordinate, any point that's along the line y equals 1, they're all going to have the same slope because they all have the same y value. So along this line where y is equal to 1, here the slope is always going to be negative 1. And sometimes it's hard to draw this completely accurately, but try and draw something that looks like maybe negative 1. Along this line where y is equal to 2, all of these coordinates would have the same y value, and so they'd all have the same slope. And so here my slope will be negative 2. Again, this is hard to make this accurate, so try to make it just a little steeper than the previous one. Something like that. Along the line y equals 3, all these would have the same slope. It'd probably be a slope of negative 3. You can see where this is getting hard to make it look accurate, but make it look steeper. Oh, that middle one looks a little steep. Maybe rewrite that one. Okay. We can do a similar thing for all of these coordinates where the y values are negative, where y is equal to negative 1. The slope would end up being positive 1 because of the negative here. So along this line, they'd all have a positive slope of 1. Along the line y equals -2, plug in -2, they'd all have a slope of +2, so a little steeper. Along the line y equals -3, they'd all end up having a slope of +3, so again a little steeper. And now at this point, you can see we have created our first direction field, our first slope field. Now the way we use our slope field is to draw what typical solutions might look like. So if I were to say, draw me a solution curve that goes through this initial value, then a solution curve would probably start up here. It would match the slope of these tangent line elements here. It would go down. It would kind of match the slope of the tangent line elements that it's next to, and it would probably end up looking something like this. If I said draw an initial condition, or the solution for a differential equation whose initial condition was here, it would probably look something like this. Down here, a solution curve might look something like this. So here we have 3 different solution curves that all differ based on what we would call the initial value problem point. Now again, for autonomous differential equations, this is great because our values, our slope field, our slopes only depend on the y value. Okay, now a little bit of review. The last thing we could do here is we could identify our equilibrium solution. Here we could say our equilibrium solution, the value where this is always going to be a slope of 0 would be at y equals 0, which we can see in our direction field here. And because of our other trajectories, the green solutions we drew, would this be a stable or unstable equilibrium solution? Here we want to be able to say it's a stable equilibrium solution, because solutions that are near it are always drawn towards it. They get closer. Okay, let's try one more. So now we'll look at y prime equals t minus y. Now this is a non-autonomous differential equation because it contains both the t and the y in your dE. So now when we do this, we have to consider what our slope is going to be at each point individually. And let's again start at the origin. At 0, 0, we'll plug 0, 0 into our differential equation. At 0, 0, a tangent line, our slope field element would have to have 0. Now I could move to 1, 0, but I like to do these with a little bit more finesse. And notice that this is going to equal 0 anytime both t and y are the same thing. So this is going to help me to think about the differential equation a little bit more holistically. Anytime t and y are the same, the slope is going to be 0. So that means at 1, 1, the slope would be 0. At 2, 2, the slope would be 0. At 3, 3, the slope would be 0. Same as at -1, -1. -2, -2. -3, -3. Okay. Now let's go to another point. Let's consider the point 1, 0. if you evaluate your DE at 1, 0, and I notice I just called this X here. This should really be T, because we're talking about a T axis. Okay, so at 1, 0, plug in 1 for T, 0 for Y. At 1, 0, this would have a slope of 1. Similarly, if I considered the point, what is this, 2, 1? T is 2, Y is 1. Then 2 minus 1 would still be a slope of 1. This would be the ordered pair 3, 2. T is 3, Y is 2. If T is 3, Y is 2, your slope is still 1. And I could continue on with all the other points in here, but I'm starting to recognize that anything along this slanted line is going to have a slope of 1. So again, if you imagine here, this point, 0, negative 1. T is 0, Y is negative 1. The slope would still be 1. 1, 1. Okay. Now I'd like you to practice drawing some slope field elements for the rest of this DE. So if you could, please pause your video and draw your rest of your slope field elements. I'm going to complete mine while the video is paused. So when you come back, you should see the completed direction field. I'll see you in a moment. Okay, I hope you completed your direction field, and it should look something like this. Now that you've completed your direction field, we should be able to draw what a couple of typical solution curves might look like. So imagine that we were to give you an initial condition that started here. Then a solution curve would have to follow the direction field elements, go through this point. It might look something like this. Another one might look like this. One down here might look something like this. Okay. Note, creating direction fields by hand is not typically done. Nobody does this. We are doing it today just for instruction so you can see how direction fields are created, but creating a direction field is much better suited for computers. However, we need to be familiar enough with direction fields to understand the output of the appropriate software that we use. Now, if you'd like to create some direction fields, you can do this with any software that you find on the internet just by Googling direction field plotter or slope field calculator. However, for your convenience, I did put one on our Canvas homepage for you to see. Let's see if I can open this with us right now so you can see it. I can't open that, so let me open up a web page. Let's go to our Canvas course. And on our Canvas homepage, under the quick links, I do put some links for slope field calculator, D-field plotter that work with Macs as well. So if you were to click on this program, it allows you to enter your differential equation. So let's enter the one that we just did a moment ago. Ours was not in terms of y and x, but ours was in terms of y and t. And our differential equation was not t plus y, but t minus y. Some of your options are you can change the window that you view your direction field on, and you can change the number of slope field elements. But I'm okay with the ones that are preset for us. Notice that this does create a direction field similar to the one that we created by hand. And if we were to click around for any of the initial conditions, it does show us what a typical solution curve could look like. If you did want to be specific, you could actually enter the ordered pair for a specific initial condition that you wanted to look at, and it would draw that one as well. Now, in your homework, you're going to be asked to submit various direction fields along with your assignments. And so the easiest way to do this is to probably print your screen or open up a snipping tool where you can just take a snippet of the direction field that I'm asking you for. And then you can insert this into any Word document and submit it with your homework. I'm going to be using the slope field generator for other problems, so we're going to get more practice with it in the next couple of sections. Okay, so use your slope field calculator when appropriate. Okay, a couple more definitions for us. So remember, a what differential equation that does not depend on time? What is the name of a differential equation that does not depend on t? So we should be remembering some of these words now. This is an autonomous differential equation, does not depend on t. It only depends on the variable y. An equilibrium solution is a solution that does not change over time. Now, previously we only talked about 2 types of equilibrium solutions. There are technically 3 types of equilibrium solutions. An equilibrium solution is stable if solutions near it tend to go towards it. So here you can see for a stable equilibrium solution, regardless of which side, above or below, you have an initial condition, they both approach your equilibrium solution. An unstable equilibrium solution is when solutions near it tend to go away from it. And this is from both sides. The one I have not previously mentioned before is sometimes referred to as a semi-stable equilibrium solution. If solutions on one side tend to come towards it, and on the other side they tend to go away from it as t goes to infinity. So technically there are 3 different types of stability we talk about. Okay, let's look at another example of our direction fields. This one again is very specific because I want to talk about it in different ways. The first thing I think we should notice about this differential equation again is that is this autonomous or non-autonomous? So remember, when asking the question about autonomous or non-autonomous, you want to be able to know whether or not it depends on the variable t. Here, since t does not show up, we know that this is an autonomous differential equation, which makes the direction field rather easy to draw. But I want to add something to our direction field referred to as the phase line. Now, the phase line is not discussed in our textbook. However, I think the phase line is incredibly valuable when looking at autonomous differential equations. A phase line is a one-dimensional picture of your two-dimensional space. The way I use my phase line is to determine what solutions look like without drawing all my direction field elements. Let me show you with an example. When we look at my differential equation, we should notice here that there are two equilibrium solutions. There are two places where our dE is always going to be the same, where the slope is going to be 0. It's at y equals 0 and y equals 2. Now on our phase line, I'll put those two equilibrium solutions, one at 0 and one at 2. Notice I'm trying to get them to be about the same space as like the line y equals 2 over here. Now because these are equilibrium solutions, we know that the slope will always be 0. So if in our direction field, these we're going to have slopes of 0 along every point in here. Same as here. Notice that this breaks our direction field into 3 regions. The things going on in this top portion, the things going on here, and the things going on here. And this corresponds to the same as the phase line. And what we should notice is that any of the slope field elements in this top region are going to have the same signed slope. Similar in this middle region, similar in this bottom region. While the values of the slope will change, the sign will always be the same. For example, if you were to pick the line y equals 1, pick this test point in this region, anything along the line y equals 1, the slope would be 1 times 1 minus 2, which would be -1. And I don't really care that it's -1 as much as that I know that it's negative. I'm trying to draw an arrow pointing down here. Similarly, anything along this line y equals 3, along the line y equals 3, your slopes would be 3 times 3 minus 2, and this would be 3. And I don't really care as much that it's 3 as it's always going to be positive. Similarly, anything in this region down here, and this is where maybe this is more instructive, is let's imagine this line y equals -1. Along the line -1, your slopes would be -1 times -1 minus 2. And I think these end up being +3. If we picked anything along this line y equals -2, then here your slopes would be -2 times -2 minus 2. Here our slopes will always have a value of 8. Anything along this line y equals -3, the derivative at -3, the slope at -3, this would be -5 right here, times -3 would be +15. Now, this can be really hard for me to draw slopes of 3, 8, and 15 on here, but what I do notice is that while they're all different, they all have a positive sign. So they all would be moving upward. Now again, this is only for autonomous differential equations. Because now if I want to draw some typical solution curves, we know that solution curves in this lower region are always going upward. So solution curves would have to go something like this. Or another one might go like this. Anything in this middle region always have to have a slope that's negative. So they might go like this or like this. Anything in this top region would always have a slope that's positive. And so they may look like this. Notice I'm able to come up with our qualitative analysis of these solutions just by knowing the signs in each of these three regions. I do not have to draw every slope field element. Your phase line will also tell you the stability of your equilibrium solutions. Here, for the equilibrium solution at y equals 2, I can see solutions go away from it, from both above and below. This would be a unstable equilibrium solution. While at y equals 0, solutions from both directions come towards it. This would be a stable equilibrium solution. Okay, I have one more example to look at with you today, and this would be a matching exercise. So in this problem, I would like to match each of the following differential equations with its corresponding D field. Now, there's different ways you can do this. You could do them point by point. Or you can use what you know about the signs of your differential equations or the value at specific points to help you predict it. For example, this one at t minus y. Earlier we saw this and we said, well, anytime that y and t are the same, the slope will be 0. Anytime that y is bigger than t, the slopes will be negative. Anytime that y is less than t, the slopes will be positive. So there's different ways you could try to imagine this. But I'm going to use the fact that anywhere that y and t are the same, the slopes will be 0. So in our direction field down here, that would be at maybe 0, 0, 1, 1, 2, 2, 3, 3. The slopes are all going to be 0. Using this, I'm able to say that this probably matches direction field C. Let's look at y prime equals y. The way I look at this one is your slope is always the same as the y value. Also notice that this is autonomous. It does not depend on t. So any horizontal line where y is the same, it doesn't matter what t is, the slope is always the same. So I'm going to use both those ideas here, that your slope is your same as your y value. Also, you can think that if this is a positive y value, you have a positive slope. If you have a negative y value, you have a negative slope. So here I'm drawn to graph D. Notice along this line y equals 1, these all have the same slope, and it's always positive. Y equals 2, these all have the same slope, and it's positive, and it's steeper than the previous. While if your y value is negative, the slopes are negative. If your y value is negative 2, they're even more negative. So just looking at the signs and the slopes, I'm able to say that this has to be direction field D. Okay. This first one. Again, there's different ways you can do this. When I look at this first one, I notice that this differential equation does not depend on y. It only depends on t. Now, don't say that the slope is 1/2, because it looks like y equals mx plus b. That's not true. Here, you tell me a value of t, and I'll tell you the slope. But notice that because it does not depend on y, every value of t, or every point on your graph where t is the same, like maybe this vertical line, regardless of what y is, your dE only depends on t. And on these lines, t is always the same. This is the line t equals 1, the line t equals 2, the line t equals 3, t equals 4. Let's look at t equal 2 for a moment. If t is equal to 2, yes, all of these have different y coordinates. That's true. But along t equals 2, when you plug in 2, these are always going to have a slope of, well, it'll be 1/2 times 2 plus 1. These will always be 2. The slopes are always 2. The slopes are a little steeper. The slopes are a little steeper. Also notice anywhere along this line here where t is -2. Well, if t is -2, this would be 1/2 times -2 plus 1. This would be -1 plus 1, or 0. So anywhere along this line, the slopes are always 0. This helps me deduce that this has to be the direction field for B. And by elimination, we can determine this has to be for A. Again, you could use different methods for picking points. Notice that if t is ever 0, then this fraction is always 0. So anywhere along the line t equals 0, the slopes are always going to be horizontal. Or you could pick points, like maybe the point 2, 2. If you pick the ordered pair 2, 2, this would be negative fraction 2 over 2, or -1. So here my slope would have to have a -1. Or if you pick the point 2, -2, there's your negative. Now you're here, your t value is 2, your y value is -2. This would end up being +1. And notice here your slope field would have a slope that's +1, which will allow you to deduce this is graph A as well. Now in your homework, you have a couple of matching problems like this you're going to have to do. Try and think of it holistically or by points to help you determine which graph is which. Okay, this is going to be the end of our video for chapter 1.2. I hope this is helpful. If you have any questions, please reach out to me, or else I will see you in our virtual lecture when we talk about this next. See you next time.